Hello, I'm going to talk about a unified sparsification approach for matching problems, and this is joint work with my student Lazar Milenkovic. We are interested in the maximum cardinality matching problem, or MCM for short, and such a matching can be computed in any graph within m root n time, but getting a 1 plus epsilon approximate MCM can be done in linear time using the same classic algorithms, and our focus will be on 1 plus epsilon approximate MCM. So now you have some input graph G, and you would like to compute a 1 plus epsilon approximate MCM. One way is by running the classic algorithms. The approach that we will take is to first sparsify the graph into a subgraph that we will call a matching sparsifier. Let's call it H on M prime edges. M prime should be much smaller than M. And then we are going to run some approximate MCM algorithm on top of the sparsifier, which is going to take time linear in M prime rather than M. And the approximation guarantee will be 1 plus epsilon, but with respect to the sparsifier H. So we say that H is a 1 plus epsilon matching sparsifier for G if it preserves the maximum matching size of G to within a factor of 1 plus epsilon. So if H is indeed such a sparsifier, then the approximation guarantee is actually 1 plus epsilon squared with respect to the original graph. And this is roughly 1 plus epsilon. And the question is whether we can compute such a 1 plus epsilon matching sparsifier in sublinear time, ideally in time linear in the size of the sparsifier, M prime. And we will be able to get such a result by focusing on the family of bounded neighborhood independence graphs. So what is this parameter that we're going to denote by beta? And beta is going to take values from 1 through the number of vertices minus 1. Beta is the maximum independent set size in the neighborhood of any vertex. So for example, if you look at the blue vertex here, it has 6 neighbors, and in the subgraph induced on them, the maximum independent set size is 4. And in any other vertex, looking at the neighborhood of such a vertex, you'll see that the maximum independent set size there will not be bigger than 4. And so beta for this example is 4. Now let's look at more canonical examples. The n-click, it has beta 1, minimum possible beta. The n-star has beta n minus 1, which is the maximum possible beta. And you can see also that there are dense graphs with large beta. And in general, you can notice that there is no direct correspondence between the density of the graph and the neighborhood independence parameter beta. This family of graphs has been studied in various research areas, such as structural graph theory, and sometimes by different names, such as the family of claw-free graphs. And it includes all line graphs, Nominees graphs, and other interesting graph families. And there is a growing body of work on this family of graphs and subfamilies. And most relevant to us are 2 papers that I'm going to discuss now. The first is by Asadi, Chen, and Khanna, where they showed that a delta plus 1 vertex coloring can be computed in n root n time. This is a tight runtime bound up to some polylog factor. And they also showed a quadratic runtime lower bound for the MIS, the maximal independence set problem, and the maximal matching problem. In the follow-up work with Asadi, we gave a simple deterministic algorithm for computing an MIS in beta n time for graphs with bounded beta. And we also showed that one cannot do better than that. So beta n runtime is tight for MIS. For the maximal matching problem, we gave a randomized algorithm running in similar time with a slack of log n on the running time. And we also showed that randomization is crucial. We gave a quadratic runtime lower bound for deterministic algorithms. And we also showed that a lower bound of beta n on the runtime holds here as well. So other than shaving the log n slack in the runtime, there are two other questions. First, can one get a parallel or distributed algorithm for bounded neighborhood independence graphs? And let me mention that the algorithm by the AS19 paper is inherently sequential and centralized. And second, a maximal matching provides a 2-approximate MCM. Can one do better than that in terms of the approximation guarantee? And this brings us to our results. So we use the following surprisingly simple algorithm where we take for every vertex in the graph delta random neighboring edges without replacement. And then that's it. We just take the union of those sampled edges and we get a 1 plus epsilon matching Sparsifier. We are going to call this subgraph G delta, the random Sparsifier. And of course, I didn't specify what delta is. It's going to be roughly beta over epsilon. And the main theorem is that if we take delta to be slightly bigger than beta over epsilon, then G delta is a 1 plus epsilon matching Sparsifier for the graph G with high probability, provided that beta is slightly smaller than n. And when beta is very close to n, we can use a slightly different approach to get a 1 plus epsilon matching Sparsifier, but I'm not going to talk about this detail. So let's assume that beta is smaller than n by at least a factor of log n. And you can see that the size of the Sparsifier grows linearly with beta, but if you remember, this is inevitable by the lower bound on the runtime that we saw before. So in other words, this density is optimal up to the epsilon dependence. And since this construction, G delta, is as simple as it gets, we can implement it efficiently in several basic models. And in particular, you can notice that the choices that we make for one vertex are independent of other vertices and can also be done in parallel. So we can implement the construction efficiently, not just in sequential or centralized settings, but also in parallel and distributed settings. And so I'm going to cover some concrete applications in the next slide, but I want to say that more broadly, we should be able to apply this random Sparsifier construction in settings where there are some underlying space constraints, such as the MPC and streaming models of computation, as well as other models that you can think of. So now I'm going to talk about some concrete improvements over previous work. The first is in the classic sequential setting. So I didn't specify the exact model, but it's the standard model that you can think of. And what we get is a 1 plus epsilon approximate MCM in time, roughly linear in the size of the Sparsifier. So once you have this Sparsifier, you need to work on it, right? So We're applying the classic algorithms on top of it. And so the running time is 1 over epsilon times the size of the Sparsifier. And comparing this to the previous result, there the matching is maximal, so the approximation is 2, and the running time has a slack of log n. And let me remind that beta n is the tight bound, and in this way, beta is the right parameter for approximate MCM in the classic sequential setting. Now, for free dynamic graphs, and I refer to the standard setting of dynamic graph algorithms where in each update step, a single edge is either inserted or deleted. And we would like to update the graph structure of interest and approximate MCM in this case as fast as possible. And we get the 1 plus epsilon approximation with update time roughly beta. And in the previous work by Berenboim and Maimon, they got a deterministic algorithm for maintaining a maximal matching and therefore a 2 approximation. And their update time is square root beta n. So it's at least square root n, even for constant beta. And so we get a polynomial improvement in almost the entire range of parameters. In the standard distributed message passing model, in the local model of computation, we get a 1 plus epsilon approximate MCM within log star n rounds. And the previous deterministic algorithm by Berenboim and Oren gives, in the same number of rounds, a 2 plus epsilon approximation. And I also want to mention that a nice feature of our distributed algorithm is that it achieves a sublinear message complexity, which is a rare feature in distributed algorithms. So now I will go over some of the high-level ideas in the proof of the main theorem that G delta is a 1 plus epsilon matching Sparsifier. Take any graph G and any MCM M for it, and now W will denote the set of matched vertices. It's going to be the world that we will try to focus on, and F will be the set of unmatched or free vertices. And notice that F is an independent set in the graph. Now consider the subgraph of G delta, the random Sparsifier, induced by the matched vertices of W. There we take an MCM, let's call it M delta, and these are the green edges in the picture. And the claim is that M delta, which is a matching inside G delta, is a 1 plus epsilon approximate MCM for the entire graph. Okay, so let's denote by WF the set of free vertices under the new matching M delta, and WM will be the set of matched vertices under M delta. We would like to argue that WF is very small, meaning that almost all the vertices of W are matched also with respect to the new matching. And the proposition is that the size of WF is at most epsilon over 2 times the size of the entire set W with high probability. And notice also that WF, the set of free vertices here, forms an independent set in the random Sparsifier G delta. Now, to prove this proposition, we are going to show that the complementary event, where WF is bigger than this, holds with low probability. And we'll do this in a few steps. The first is that we'd like to argue that without loss of generality, it can be assumed that all the vertices of WF are of high degree, higher than delta. and delta is the parameter of the Sparsifier. So why should this be true? Consider any low degree vertex X inside WF, if any. Now, because this guy is of low degree, all the edges incident on it are taken to the Sparsifier, including the matched edge in M, in the original matching. So now we can take this matched edge to the new matching and delete another edge in its place. So we are making a swap. We didn't reduce the size of the new matching M delta in this way, but we move X from WF to WM. And we can repeat this process for as long as needed so that in the end, no low degree vertex will belong to WF. And this is not the formal argument, but that's the high-level idea. So now, in the second step, consider any vertex V in WF. We say that V is good either if its degree inside W, and let's focus on W, is at most some constant C times beta over epsilon, or maybe its degree is larger than that, but then we require that a good fraction of its neighbors lie inside WF. That's the meaning of this condition. And building on the AS19 work, we can show that at least half of the vertices of WF are good. But now remember that all the vertices of WF are of high degree, higher than delta. And at most, beta neighbors could come from F because F is an independent set. So now because delta is sufficiently bigger than that, the consequence is that for every good vertex, the second condition here must hold, meaning that a good fraction of the neighbors come from WF. And this is a good fraction in the sense that it's not too small. Okay, it's a constant fraction when epsilon and beta are constants, and in general, this ratio depends on epsilon and beta. Okay, so now in the third step, our goal is to analyze the probability that WF is in the independent set. So for this to be true, for any good vertex, V, none of its edges, adjacent edges that lead to WF can be sampled to the Sparsifier. What is the probability of this event? Well, because delta is large enough, the probability of the event is at most epsilon. We can show that. And then V is just one good vertex out of many. The number of good vertices will be at least this. And we get this lower bound because we are in the situation that WF is of big size, bigger than epsilon over 2 times W. So we get this lower bound on the number of good vertices, and we get overall this upper bound on the probability that WF is an independent set of big enough size. And then we use one more observation and get that this probability is polynomially small. And I'd like to say that we are done, but we have ignored here an important point. The vertex set WF is a random set which depends on the randomness of the random Sparsifier. And this means that when thinking about the calculation from the previous slide, it was inherently flawed. To remedy this, we are going to fix an arbitrary subset U of W, and this subset should be of big enough size, at least or bigger than epsilon over 2 times W. And then we are asking, what is the probability that this fixed subset U will be independent set in G delta and of big size? And here we use the upper bound from the previous slide because now it will be okay because we fixed U prior to constructing G delta. And the probability here is so slim that it can absorb a union bound over all possibilities of U for WF. And this is how we fix this issue and get the required result. To conclude, we presented a unified sparsification approach via a surprisingly simple algorithm that can be implemented efficiently in several settings. And in particular, we managed to improve previous results in those settings. But we believe that this approach is of broader applicability, especially in settings where there are inherent memory constraints. Now, if you remember, G delta is of size that grows linearly with beta, but as we mentioned, this is inevitable due to a runtime lower bound of omega n times beta for the sequential setting. And this suggests that beta is the right parameter for the problem of approximate MCM, at least in the classic sequential setting. There are quite a few interesting questions for future work. One of them is to nail down the exact dependence on epsilon. And right now, the dependence is roughly linear in 1 over epsilon, but perhaps it could be improved to, say, a polylogarithmic in 1 over epsilon. What should we do when beta is unknown? Right now, we are setting delta to be roughly beta over epsilon. When beta is unknown, things are more intricate, and we are exploring this direction. We already have some results. And in particular, for the sequential setting, we don't need to know beta. So we are sort of guessing what beta is in a non-trivial way. And the next question is whether this sparsification paradigm can be applied to more models, such as the models that I mentioned before, or other models. And here too, we have some preliminary results. And finally, maybe this approach of sparsification in bounded neighborhood independence graphs could be applied to other problems outside the scope of matching problems. And I'll stop here. Thank you.